All right, we are live. Hello everyone, welcome to Intro2Astro 2022. This is the first of our 8 online sections. My name is Fei Dai. I'm a postdoctoral researcher at Caltech, and I am your host and the co-organizer of the workshop, along with Howard Isaacson, who is a research scientist at UC Berkeley. We are also joined here today by several mentors, and the mentors will help us present the course materials and answer the questions from students. So why don't we go around the room and do a quick round of introduction. Howard, why don't you start?
Thank you, Faye. My name is Howard Isaacson. I work at UC Berkeley in both exoplanets and SETI, and happy that everyone's going to be here and looking forward to it.
Thank you, Howard. So, tip for the mentors, could you mute your YouTube video when you're presenting, because there's some feedback there. All right, Anamitra?
Hi, Anamitra here, and currently I've completed my graduate studies and I'm into research in exoplanet science. Nice to see it for the second time. Yeah.
Thank you, Anamitra. Chetan?
Hi, my name is Chetan. I hope you can hear me. I am currently a business tech analyst, which is a data analysis role at ZS. And I'm also working as a research intern with Dr. Alex Tichy at Academia Sinica in Taiwan. My main focus area is exoplanets, and what my research revolves around is detecting exoplanets using tests and in the continuous swing zone of tests. And that's it. That is about me. Thank you.
Thank you, Chetan. You know, everyone, let's take a break. I think I might have not muted myself. I think I have. All right, let's move on. Rishabh?
Yeah, hi everyone, I'm Rishabh Srivastav. I'm an undergrad student at IIT Madras. And currently I am at UBC Vancouver working in cosmology under Professor Douglas Scott. Nice meeting you all.
Maria?
Hi, my name is Maria. I just finished my first year as a grad student at the Institute for Astronomy in Hawaii. My research area is primarily planet formation, and currently I'm working on high contrast imaging of protoplanetary disks.
Thank you. Tim?
Hello everyone, my name is Dr. Tim Holt now. I recently graduated from University of Southern Queensland with a PhD in astronomy. I work primarily on asteroid dynamics, including Jovian Trojans, but I also do a little bit of work on dynamics of exoplanet systems. And I'm primarily interested in also a lot of taxonomy stuff, so how things are related to one another. Despite the accent and the affiliation with the University of Southern Queensland, I'm actually based here in Boulder, Colorado.
Cool. Thanks, everyone. All right, before we delve into the technical topics today, let me give you a quick overview of the course. Intro2Astro is a free online program. The aim of our workshop is to help aspiring undergraduate students, as well as astronomy enthusiasts in general, to get a sense what astronomy research is like in the real world. We'll cover topics such as coding, reading scientific papers, research methodology. For example, in week 4, we will try to recreate some of the discovery of transiting exoplanets using the NASA TESS mission. We will also cover soft skills such as preparing your CV, preparing a personal website, as well as applying for graduate school. Hopefully, some of you will have a funded summer research position next summer, or even end up working as an astronomer in the long future. We're very proud to say that some of our previous participants have successfully done so. So to motivate you further, our mentors have kindly agreed to share their personal stories too, so that you'll see having astronomy as a career may be easier than you think. Of course, you're most welcome here if you're just here for fun or to pick up some astronomy knowledge. This is the 5th year we are organizing this workshop. Believe it or not, there are more than 1,000 of you who sign up for the workshop across the US and around the world. and we are really excited to have all of you here with us. Feel free to use the chat window to pose any questions or to interact with mentors. Let me show you a few things that we'll be using for this workshop. First of all, this is our course website. You can find a lot of useful information here, like a brief overview of the course, as well as links to course registration, as well as a GitHub repository in which we'll distribute the weekly assignments. And there is also a link to our YouTube channel. After the class today, we will upload the recordings to YouTube so that you can view it at a different time. Another thing I want to mention is piazza.com. This is an online forum for students of a certain course. Since there are more than 1,000 of you who sign up for the course, this may be the best way of handling questions and answers. So if you have any questions related to the class, please feel free to post here, and the mentors will take a first step at answering these questions, and other students can also answer the questions here. You can also share useful information here. Feel free to do that. The last thing I want to mention is that our course is also recorded on GitHub. The link is provided in the course website. Here you will find the weekly assignments as well as the readings, the reading assignment for each week. All right, let's go back to the Zoom. Throughout the course, our lectures will actually be Monday 5 p.m. for the next 8 weeks. And this time seems to work relatively well for people across different time zones. But don't worry if you cannot make it to lecture. Again, we will be posting the recordings on YouTube. All right, I think that's most of it. Howard, do you have anything to add?
Nothing for me, thanks.
Cool. All right, without further ado, the first topic today is coding with terminals using Unix and GitHub. And our presenter is Chetan. Let me hand it off to you, Chetan. Feel free to start sharing your screen.
Yep, thank you so much. Can you see my screen right now and the slides?
Go ahead.
So hi everyone, as I already introduced myself, my name is Chetan and I'm a data analyst at ZS and a postbac research intern at Academia Sinica. And I'll be talking about Unix and Git. And these are the slides referenced a bit from 2021 slides by Joey Murphy. And the images are sourced from either the Unix Software Carpentry, which is one of your assignments, or there are screenshots. So let's start. What basically is Unix? Unix is the first portable operating system, and what an OS is basically something that it makes an interface between the hardware of our machines, our laptops and our computers, and the software of our machines, and it lets us, the users, interact with the machine. So it was written up in 1971 in the C programming language, and it is extremely fast for like repetitive tasks and doing stuff like file manipulations and making, there are some scripts in which we can put commands of Unix in, which we'll be talking about in the next part. And Mac OS by default is Unix, and Linux is also a Unix-like alternative. But for Windows, we'll have to do some special handling that we'll be talking about later on as well. So first of all, let's talk about what is Unix shell. And this is the term that you'll come most across. So Unix shell is kind of an interface or a program that we write our commands in, and it is a command line interface and a scripting language. And that means that we can write commands in this Unix shell and it will execute it and give us some output or whatever we desire from it, like maybe a file manipulation or maybe opening up our document, writing a new file and stuff like that. And Bash, this born again shell, is one of the most popular implementations of Unix in Unix shells. So when we write a command, we have to write them in a particular syntax that is accepted by this shell. And when we can also combine these commands together to make a script, which is kind of a program to accomplish larger tasks. And macOS's terminal, the application on your Mac, would give this command line interface for you. And Linux also has this similar thing. You can open up a terminal in Linux and you'll be good to go. For Windows, you can either install a Git shell, which is kind of doing similar things as Unix, or maybe install your Linux subsystem for Windows, which is to say you are just importing a new Linux subsystem on the whole Windows thing. So this is these two you'll have to do on your own. The instructions are over in the links in the slides. But in our Jupyter notebook today, we'll be looking up at magic command %% bash, which allows us to run the shell commands in the Jupyter notebook itself. So here is just an image of what a terminal looks like. And you can see this is this shell. This is the shell that we are talking about. So whenever we open it, we'll see this percentage or maybe a $sign, which is a prompt, which is saying that it is asking for an input or waiting for an input from the user. We write a command and then execute it pressing enter key. So the first command that we are talking about today is pwd, which is telling us the present working directory. And whenever you open up a terminal, you'll see this umlaut over here, this symbol. And this means that you're in the home directory. And you can also check this using the pwd. So the home directory is the user's home directory. So basically a /user/Chetan Chawla, that is my name and that is my home directory in my laptop. So why is there like a slash in the beginning and why is there this structure? So this is the file system that Unix is built upon, in which there is a root at the whole tree structure, which you can see on the bottom here. So the whole file system starts with a root that is represented by the slash, and then there are directories, or you can also call them folders inside this root folder. And then we were going in the home directory, so it is something like this. Let's say that this is my home directory. Then my path to the home directory would become /users/ whatever my name is. Or if I were to access a file in this folder, in my home folder, it would be just like /users/my name and /the file name. And as I said, this symbol, this umlaut, represents the user's home directory, and terminal by default opens it whenever we open it from our Mac or even from Linux. Then how would we like move across these directories? So the command for that is change directory, which just changes our working directory from one to another. And we can always go back to our home directory using this cd space umlaut again. And we can check where we are using the command pwd. So if we were to like run it in our Jupyter notebook, we'll see that we'll do just %% bash to, this is the magic command that makes our Jupyter notebook cell work like a Unix shell. And then we write pwd after moving or changing our directories to home, and we can see that we are over at our home directory. Similarly, we can also do some more stuff over here. So let's say that there is, since we are running is on our notebook, the pwd command by default goes to the folder that this Jupyter notebook is in. And that would be something wherever my folder is made up over. And then we can also check the contents of the folder or the directory that we are in using this command ls, which is to list the contents. And these are all the files that were present in my folder at that time. So how are these commands useful? We can move from directory to directory using these, and also make or change the directories based on where we are. So these are some useful commands that you can look at whenever you get time. But overall, if I were to like summarize it, this cd double dot would say that we can go one step up in the tree in our Unix file structure. The cd dot says that we are in the current directory. Cd slash would make us go to the root directory, since slash is the indication for the root directory. Cd, if we were to write this or just cd, we'll go to the home directory as we talked about earlier. A cd- would change us to whatever directory we were working in before this. And we can also write the directory name directly. So these are relative paths because these are working on where we are currently, but we can also give them absolute paths. So if I were to go into my astrophysics folder that is present in my home directory, I'll just put on the whole path to that folder, and that will automatically take me to there wherever I am in my system. So this is one thing that's also useful. And you can see a demo of it here. So we were in this astrophysics folder. We went to the home using the CD umlaut, and we checked using pwd. We were in the home. Then we went to root. Then we again went to home, and we used ls to list the contents of this folder. We saw there is this astrophysics folder in here. We went to this astrophysics folder, and then again we went back one step. So dot dot, that means I'm again at my home directory. CD dot would do nothing since it says that go to the current folder, which is again this home folder. And then I'm just in the end giving this whole command for a whole absolute path, and I'm in this folder, see astrophysics in my home directory. And the last command is the cd again just makes me go to the home directory, and the cd hyphen would make me go to the last working directory, which is in astrophysics. So we can also do some more things with listing contents, and these are done by flags. So flags are just options that we pass on to our commands, and we can like say that ls-l, that would give me the directories and the files in the current folder in a list format. If I were to just write -t, it would organize or sort them by the time they were created or modified. And we can also, combine these flags to make a composite flag. So if we were to say ls-ltrh, here this L would mean that list the directories in a file format, in a list format. The T would say sort them by time. The R here says in reverse order, and H here says in human readable format. So the sizes are in KBs and MBs, so that it's easier for us to understand. And we can also see these flags using this man command. So man is this manual command, and in Linux you can also write --help. And for whatever command we want these flags for and the whole documentation for, we just write the command name over here. So you can see if I were doing ls-ltrh, these are all the files that are present in a list format. They are sorted by time, so you can see like these are arranged in a reverse order of time. So June 12th, here it is the latest file, and then March 2, here is the oldest file. And then H means the human readable format. So this is just writing stuff in like bytes, kilobytes, and so on, and not. So this is the H flag. And moving on, we can also create files and directories and delete them. So touch is the command that just creates an empty file. mkdir is make directory command that just creates a new directory. rm would delete a file, and mind this is permanent. This is permanent, so only try this on a temporary file. If we were to remove all the contents in a directory, and it's not an empty directory, there is content in the directory, we'll have to use the -r flag, which is just to say delete everything recursively, so until everything is finished. But again, be careful with rm. This can make you delete really important stuff, and it won't be backed up anywhere, and it can even make you delete your whole OS. So be very careful. You can use this -i flag, which requests for confirmation before deleting. So this is the interactive flag, and this is something that is advisable. So if you're trying this, please make sure that you look over here. Moving on, so similar to touch just creates an empty file. But if we were to edit a file, there are built-in text editors in Unix shell. So Nano and Vim are two of those, and these are built with more complex capabilities. So this is Nano. This is a screenshot of Nano. You can see like we have these shortcuts on the bottom that we can justify our whatever we are writing. We can read a file. We can move in between the file and write anything over here. So this is just to edit a file or create a new text file or whatever you want to. Then moving on to copying and moving. So we can copy some source file to a target file using this cp command. Similarly, we can move files using mv command. And if we were to copy everything in a directory, you will have to use this -r, which is the recursive option. And for move, again, we have -r. A move is also used for like renaming files. So you can just move something and change the name of the file in the same folder. And then for printing to screen, we use the command echo. Here we can write a message or a string directly, or we can write a variable. So whatever the value of the variable is, let's say we have written above this, that variable is equals to 2, it will echo 2 using this $. And while we are working with file, we can print the commands of like print whatever the contents of the file are using cat, and then if the file is too long, we can use this head command or the tail command to like display the first 10 lines or the last whatever lines we give using this -n flag. And then there are some operators which are also useful. So cat and then this operator, single one, will override the contents of a file starting from line 0. So this is one kind of an operator. If we were to append the contents or whatever we are writing to a file, we'll use this two, greater than signs. And similarly, there is one pipe operator which passes the output of one command to another. So let's say that I am using head and then file, the first 10 lines of file, and then using another command that is to say echo. What it will essentially do is pass these 10 lines to the echo command, and that will do whatever function it is supposed to. And then these are some extra commands that you can look at on your own. So I'll not go into these. These are pretty self-explainable, and we might go out of time if I go explaining these. But in conclusion, the general format of our commands is this is the prompt in the beginning that is saying, the shell is saying that I'm expecting an input from the user. This is the command ls or whatever we are writing. This is the option that we write using one hyphen or double hyphen for whole words. And then we'll present the argument, which can be the path or whatever that we are using. And then we can also, as we talked about earlier, that we can also combine these commands to make scripts. So these are just sequences of scripts. And I've made this small script, which just makes, so what this script does is it echoes, and this is the override operator. And so it echoes a blank file that is notebook names.txt. We could also use Dutch here. And then for all the notebooks that are present in my current folder, this star is the operator which says every word that is possible for every length. So, and this for is a kind of a loop that does stuff in a loop. So do echo $nv, which dollar says that whatever the file's name is, since it just tells the variable name, and then double greater signs. That means that write the name of the files which have the extension ipynv, which is the Python notebook extension, into this file that we created, notebook names.txt. So when you are trying this out on yourself with yourself, so you'll have this Python notebook and you can run this and you can see what happens in this file in your file system. So this is the assignment 1 and assignment 2. So assignment 1 is pretty simple. You'll have to create a new directory, change directories to this new directory, write some string in a text file, and then display the contents of the text file, and then make a copy or a backup and place it in a subdirectory. So these are the steps that you'll have to make, and these are all one command steps. You can also write these, and I'll be uploading a key for this assignment next week. You can write your script here. And then the assignment 2 is you'll have to complete this software carpentry course for Unix. This also discusses everything that we have talked about in a lot more detail so that you can understand whatever we talked about today and go through at your own pace. And moving on to the second part of the tutorial, that is Git. So Git is basically a version control system, which says that whatever project that you're making, we need to version it as we change it, and so that it is easier to maintain and revert back up to the older changes after we make some whatever changes to our code. And it just maintains a whole history of whatever we are doing, and it also makes us really easy to collaborate. So these are some terms that are related to Git. One is this Git repository, which is just a folder that you are making and having your codes in, that is alongside with a .git subfolder that gets made when you use this command git init to initialize this folder as a Git repository. So what this essentially means is that you have a folder which has some code, and now you want to track the changes in your code. So you make it a Git repository using git init that makes this .git subfolder in the repository, which is the track of all these changes. So for installation for Mac users, it's already present. You can also check this using this git -- version in your terminal or in this notebook itself. For Windows and Unix users, you can just go to this site and you can just follow the instructions. You'll get the you get the Git on your system, and the rest of the steps are the same. So these are some more useful commands that you might be using when you are doing this course. So git status tells us the current status of all the files in Git folder. Add would add the files to staging. That means that they are ready for committing now. And git commit is basically like a checkpoint in a video game. So whenever you are done with some part of your code and you are ready to commit that code as a checkpoint, you write a git commit and then add a message that is helpful for you to remember what you changed over here. And then git push and git pull, these two are commands that help Git connect with GitHub. And what GitHub is an online repository. Let me just skip over here a bit. So GitHub is an online repository that hosts all our Git repositories on either public or private servers, and it allows us to like collaborate with people and create our changes throughout and make a history of all the changes that are made by all the people in this same Git folder. And you can create your account on GitHub. So coming back to push and pull. So push means that you are pushing your local changes to GitHub. Pull means you're pulling those changes from GitHub to your own local system. And pull would be really helpful. I'll get to that in a bit. But before that, this is a kind of structure of a Git. So again, this is also a tree-like structure. So let's say that this is a branch. Branch would just mean like one single history line of a Git. And then once I made some code, I committed it at commit 1. Then I made some more progress, I committed at 2, and so on. And at fourth commit, I introduced a bug, but I didn't realize it at then. So I just kept on committing it for 5 and 6. And over here, I saw that, okay, something is going wrong. And I saw that that was committed in 4, that file was committed in 4 commit. So I can just easily go back over this and fix it because I have this whole history of commits over with me. So this is how Git is really useful. And now last part of the tutorial is just we can navigate to this our repository, that is our current repository Faye talked about. So this is the Intro2Astro 2022. And what we can do is we can go over this green button that says code, and we can copy this link, and over on our terminal, we can paste it with the command git clone. So Git clone does is it fetches this remote Git repository into our local system for the first time and makes a folder in our system. So this is something that you should do. You should go to this site and clone it on your own local system so that you'll have the whole repository with you. And then whenever you're making changes in some files, you can just add that file name or commit. So this is something that you can do on your own if you want and whenever you want at whatever frequency you'd want. But make sure to pull new changes every week, since the instructors and the mentors would be adding in the tutorial materials every week. You should do a Git pull that would fetch the latest changes from the repository onto your local so that you can work on them. And the answer keys, as I said, would be posted next week. So yep, this is all there is from me. Thank you so much.
That was just excellent. Thank you so much, Tom. I don't think we have time for questions, but if you have burning questions, please post it in the chat window. We'll take try to answer them. If not, you can also post questions later on piazza.com for more detailed questions and more detailed answer. All right, let's move on. Our next speaker is Maria, who's gonna tell us about Python and Jupyter Lab. Maria, you're muted.
Yeah, just a sec. I'm just going to share my screen. Hang on, just a minute. Okay, I trust you can see my screen and hear me okay.
Looks great. Go ahead.
All right, so today I'm going to be talking about just giving you a very, very basic introduction to what Python is, what the notebook architecture is, which you would be utilizing throughout the duration of this course. My name is Maria Vincent. As I introduced myself earlier, I'm a graduate student at the Institute for Astronomy. So this generally falls. So for those who have checked out last year's tutorials on the course website and GitHub, it follows the general structure of the course of this tutorial, which was taught by Chetan last year. So yeah, here it goes. So what exactly is Python? To put it simply, it's an object-oriented programming language, which is quite easy and very beginner-friendly compared to a lot of other programming languages out there. Compared to C++, IDEO, Java, which is not very intuitive. Python is Python because of its quite simple syntax, because of how very closely it relates to just regular English sentences. Like if you want to display something, you would just say print so and so. If you want to add something, you would just do the number plus the other number, or the variable plus the other variable. So it is very easy to understand because of its simple syntax. It's beginner friendly. And there are a lot of resources available. There's a lot of open source software modules and packages suited for various scientific and data purposes, which is why it's very popular. It can be used for data analysis, machine learning, to develop websites, to develop these automated scripts that just runs through rows and rows and rows of numbers. It can be used. Python's also used to create prototypes of softwares and to test it, and just for general everyday tasks, just to make some amount of processing and system operations a little easier. And fun fact is that it got its name from Monty Python's Flying Circus, just because the creator really liked the show and he wanted a name that was short, something mysterious that would immediately strike a chord with its users. So Anaconda, Miniconda from the many emails and messages on the course Piazza. So let's start from the basic. Conda is an open source package management system and environmental management system. What that means is it is basically this huge sack that contains a lot of different elements of creating and creating and distributing software. It was primarily created for Python, but you can also use it for pretty much any language. Most people use it for Python and R. It comes in, it lets you sort of shift between different programming environments. And by that, what I mean is within your, so you can think about it as like, within a little city, you're creating these different buildings for different purposes. Within a city, you have a school for teaching, you have a hospital that takes care of the sick, you have a building for people to live in. In the same way, within Conda, you can create different environments that all have the same base way of operating, except that you might have some slight differences maybe between Python versions. Maybe you want one environment that has an older version of Python because some software can run only on an older version of Python. In another environment, you have a newer version of Python plus some extra modules because it operates differently. Then maybe you can have an environment just for astronomy because you have all the astronomy related packages. Now, what are packages, what are modules? You'll be slowly learning that over the course of the next few weeks. So I'm not going to dive into that real quick. But what you need to understand is just that Conda is very important because that's how you create your various environments. You manage your environments, and you can also install the various the open source packages that you need to write or run a Python software, a Python program. Anaconda is a single distribution system. It basically is, so you have Anaconda and Miniconda. I'll explain the difference between the two. Anaconda is a single distribution system. It already comes with a lot of scientific packages installed for basic scientific data analysis. So you don't have to install them separately. You still have to install a few that you need specifically for your field. For some astronomy modules, they don't come pre-packaged with Anaconda, so you have to install them separately, but most things do. And as I mentioned earlier, even in Anaconda, you can create these different environments to run Python differently or to add different packages to each. Miniconda is a much more minimalized, much more simple installer for Conda. So Anaconda comes pre-packaged with many things. Miniconda does not. It's just, if Anaconda is a mansion, Miniconda is just a little cottage, basically. It doesn't come with all packages. You can certainly install them later. So I guess the pros and cons of Anaconda and Miniconda is mostly about storage. If you have enough storage and you don't want to install things separately, just go ahead, install Anaconda. But if you have very limited storage and you just need certain packages at different points of time and you're not sure which, Miniconda is a good place to start. So I think for the purpose of this course, Miniconda is also fine. You can just go on installing the packages along the way as and when you realize you need them. So I've been mentioning these things: functions, modules, packages. So these are just very fancy words for things that you'll be using on Python, which I would give you a short preview of. But before that, you should also know how to use Python. How do we write commands? How do we write a script for automating some process? So you can use Python on terminal or command line. So as Chetan mentioned earlier, you have these many commands to navigate between your system. You have these commands to create files, delete things. In the same way, you can use that same platform to even write Python programs, and not just for Python. It is also true for other languages, but here we'll be focusing on Python. So you could use terminal or command line if it's Windows. You could use text editors and scripts, or you could use notebooks. I'm going to show you how each of these work. So in a terminal or command line, it's basically line by line programming, meaning you write this one line of code, you run it, and then you go to the next line. You cannot just write a bunch of code together and run it all together. But the best part of terminal command line is you can see what's happening in real time. You can import things, you can import or install modules. What are modules are basically this sort of library of many subcommands that you would need, and the library usually represents one whole function. So for example, as an example, line by line programming, you can see this terminal window over here. It's basically, so over here, I've just taken two variables, A and B, and then I add them together, and I print the result, print A plus B is equal to whatever A plus B is. So because A and B was 3 and 5, A plus B is equal to 8. So you see, I've imported something called NumPy. NumPy here is a module. It basically has a lot of mathematical operations. So I import it to use functions within NumPy. So a function within NumPy is linspace, as you can see here. Linspace basically creates arrays of numbers for you. If you define the starting point, stopping point, and how many elements between that starting and stopping points. So you can import modules. you can also install them. So over here, I've tried installing a module called matplotlib. As you might infer, it's basically a plotting library. It has a bunch of functions that let you create plots and modify those plots. But I already have this module with me because I have Anaconda, and also it's a very, very basic module. And that's why I have this requirement already satisfied message, multiple of them actually. And yeah, so that's kind of one way to check if I have the module or not. But if I did not have the module, then you'll see a bunch of messages that shows how the module is being installed. So that's about using terminal or command line. The next way is using text editors, and these are kind of similar in the sense that you again write different lines of code. You can write all the functions that you need, but then you would run it together as a script. So the syntactically speaking, this is the reason I wrote syntax in the title is to emphasize that syntactically it's basically the same as running it on terminal or command line. But instead of line by line programming, it is a script programming, meaning you're just going to write a bunch of lines of code, save it as a script, which is a .py file, and then you can run it. So you have something, you can use basic text editors like TextEdit on Mac or Notepad on Windows, or you could use Sublime, which is a slightly advanced text editor. The advantage being it actually color codes the syntax. So you could see, so like a function would be a different color from an input, and then a number would be a different color from string input, like that. So you could create, but you could also use Notepad. So right over here, if you see, I created this file called sample_plot.py, where it's just a bunch of code. It's not color coded, it's simple, but you save it as .py. Then you go to your terminal or command line and you type Python, or you want to first move to the directory in which your file is saved. So I saved it on my desktop. So I follow cd desktop, and because I start from my main root directory, I go cd desktop, and then I type in Python, the name of the .py file with the extension, and when I run it, I get that plot. So I did plt.plot. So I imported this module with the submodule as plt. I plot it and I show it, and as a result, I get this figure right here. So this is using a text editor. But there are also script editors that are script editors like Visual Studio Code and Spider, which are basically these coding environments. You could write code there, you could write your script there, and within that you can actually run it and you can see your results. So after going through this, I will quickly show you that very shortly. So this is about using text editors and script editors, I guess. So this is what Spider would look like. You basically write your code, and then you can you have the option of running the whole thing, and you can see the results. So I print hello world, which is the very standard basic thing that you do when you first learn programming, and then I do multiplication over here, and I get what the product of these two numbers is. But you could also use it to display a plot, which I'll show you shortly. And if I had a plot, I could see it over here. And then there's this option Variable Explorer that lets me see what variables I have created and what's there in my memory, how much space it's taking in memory, etc. So now Python notebooks. Now, what is a notebook? It is kind of like a regular notebook where you can write things, you can draw things, you could do a bunch of stuff with your notebook, right? So a notebook is a much more flexible, much more interactive version rather than simply writing a code on a text editor. You could write a small portion of code along with rich text. By rich text, I mean text with formatting and images. The tutorial is written in Jupyter Notebook, so you can see how well formatted it is. Jupyter Notebook is the default Python notebook format. That Jupyter Notebook architecture has also been used for some cloud-based options, Jupyter Lab and Google Colab. Jupyter Lab is also hosted. It was also Anaconda thing. Google Colab, as the name suggests, it's like coding on a Google Drive. Okay, so the Python tutorial was written in a Jupyter Notebook. That demonstrates why, and I will show you quickly, and you will better understand why a notebook environment is preferred to writing your code on terminal or a script editor, and how it being interactive makes your experience so much easier and so much fun. So a quick introduction on what Software and Data Carpentry is. It is a very, very helpful website, which has a bunch of resources that is put together by volunteer instructors from universities and just independent groups all around the world. They have amazing exercises and tutorials to get you familiar with not just Python, but most programming languages that you need, including like the super new ones that have come up. And so they have exercises, tutorials, and you can also see announcements for various workshops over there, which teach you very specific computing skills. And you can pick and choose based on what your field of research would demand from you. So let's go to the Python tutorial. So this is a tutorial I've designed for you. I've begun it with some really short answers to all these questions and the things that I discussed in the slides, with screenshots of what things look like. So yes, I would first show you how Spider looks. Let's see. Okay, you can see it here. So basically, as I said, you can create Spider is a Python script environment where you can write script and you can run the whole thing without having to go to terminal to run it. You could see the results right there. So you could create plots, you could see your plots, and in the console, you could see the other text output. And whatever error messages you get, because I made a mistake by not importing NumPy first, which I later corrected. You could see my error there. So you can see all your outputs, and it's actually beautifully designed. Visual Studio Code also works the same way. Or because this is a .py file, I can, if I don't want it to be this fancy, I can just go to terminal and run it. So this tutorial, as I mentioned, has been written in a Jupyter notebook. Well, I'm running Jupyter Lab right now, just because I like it a little better. But the architecture is essentially the same. So this is a basic. This is just for you to visualize how Jupyter Notebook, how the whole notebook thing works, and to get you acclimatized to this environment, because this is what you'll be using very shortly. So you can, instead of having to run all lines of code together as a script, a notebook enables you to break your code into these little chunks called cells. So in this script, as you can see, I had to run this first part before running the second part, even though this first part over here has nothing to do with my plot, because my plot is an entirely different set of data. The things before that is an entirely different thing. But here in the notebook architecture, because we're breaking things up into different cells, I can pick and choose what cells I want to run. I don't need to run the whole thing to get to the last bit. I can run this, and then I come back to this. So let's do that. So first I import these libraries that I need, numpy and matplotlib.pyplot. What are these? Why I have written it, import something as something else, is basically I'm aliasing it. I don't want to write these big words over and over again, so I just write these little, just few letters. And referring to numpy as np and pyplot as plt, it's a very standard way of aliasing it. You will learn more about this next week. So shift and enter, I can run the cell, and for some reason it's taking a while. Okay, it did. And I can skip this if I want, because like, as I said, it's not relevant. So I'm just gonna go to the plot. And so as you can see, you have these texts that I've written following a pound sign. These are comments, and it's very, very highly recommended to do so for whatever piece of code you write. Because when you're writing code, you could imagine you're writing something for someone else to see, not just you. So you don't want to forget, you don't want to be the only person who can read your code. You want to be able to share and distribute code eventually, because that's how open software works. That's how writing pipelines work. So you would essentially want to write comments. You could write one-line comments by putting a pound sign and then writing whatever you want, or you could enclose comments in triple quotes like this. So this is to create a very basic plot, and there you go. Now this is something very basic. I can also read in data from an external file and plot that. So in astronomy, especially for those interested in observing, whenever you observe. You observe something on the sky and you save the data from your telescope, and then there's like a bunch of processing it should go through. The final result, even the observed data, is saved as something called a .fits file. .fits is the extension. So to whatever operation you need to do with that, you need to have the separate astronomy package. So astropy.io is a very, very important astronomy package. And from that, I import this module called fits. And now I can read my data using fits.get data from this image that I've saved in this directory. The writing what my directory name is, it follows the same Unix way of defining your directory, your subdirectory. So I'm going to run this cell. Oh, sorry. But now you see I get this error because I forgot to import my module. So now I run these, and now I can, so you don't need to exactly understand, I understand this might be a little overwhelming, but all you need to know is that this image is basically a giant matrix. It is a 201 by 201 matrix of data points. So like, which is like what, over 40,000 data points, each having a certain value. What the value of the data point is, it will typically be given by this thing over here. And I can technically adjust what my contrast limits are, so I can actually see what my data point is. Okay, this is curious. I don't know why it's doing this. It certainly did not do this before. Huh.
I can see the data. It's just sparse.
Okay, yeah. So I think it's probably just me seeing it then. All right, but yeah, you can adjust contrast limits. There's a bunch of stuff you can do. You can adjust contrast limits. You can adjust how much of the data you want to see. Right now, it's just restricted to a small portion, but you could define your axis limits. You could change your axis labels. You could change the image size. You could even change the color scheme. There's a lot of different things you can do to visualize the data as much as you want, as you prefer. So this is 201 by 201 is not that large of a data set. Now I'm going to show you how Python is actually much more powerful than this. So I'm going to read in a file that contains 20,000 rows of data distributed between 97 different columns. So that's 20,000 by 97. So that's like what, 2 times, yeah, that's like a lot. 2 times 10 to the 6 data points, 2 million data points. There you go. So I'm gonna read in all of that and then use 2 columns to create a scatter plot. And this you might have actually seen in the 2021 version of the tutorial if you've explored it. So this is another very, very useful library module called pandas, which is used to import and read in different files. So there's a .csv file which gives you the 20,000 closest stars from the Gaia archive, the DR2 version. The DR3 version is just come out. And so you can see how quickly that was plotted. There's like a huge bunch of data points that I plotted just like that. It might be a tiny bit faster. My computer is definitely slow. So again, you can change how you want to visualize this. You can change the size of your scatter points. You could change the colors. You could read in more data. And this is just 2 columns. I could also read in 3 columns and make this a 3D plot, which you're free to explore at your own time. So the whole point of this exercise was just to show how versatile Python is, how much data it can read in so little time, and why it is a very, very handy tool to use, and why every astronomer should know how to use Python. And as I mentioned earlier, here's a link to the Software and Data Carpentry for Python, which should give you a good idea and has a bunch of exercises to get you familiarized with the language and the environment in which you'll be working with the language. So that's all I have, and this is your assignment. I would advise you to go through this tutorial and repeat all of it on Google Colab, so it's a different environment from what I used. Make sure you understand it, and you can feel free to add your own comments along the way to explain to yourself what you've been doing. Commenting is a very useful skill because sometimes you write code and then you come back to it like 5 years later, you should be able to understand what you wrote. Now, another thing that's important is you should be able to save these images, because what's the point of creating plots that are useful, but you don't save them? And taking screenshots is not viable because the plot that's displayed in your notebook is not of a very high definition. So for saving, go to the tutorial on software carpentry and then save the plots that you create there. And the third optional exercise, which I think is fun, is to print the Fibonacci sequence, which I hope you know what the Fibonacci sequence is. And I've also given a hint here, use a for loop. What is a for loop? Again, there are tutorials, there are There's Stack Overflow. Google's your best friend when it comes to coding. And again, comment your code. So yeah, this will be uploaded on GitHub. This resource is available for you, and you feel free to ask questions, and the moderators are there to help you out. Thank you.
Thank you so much, Maria. That was fantastic. All right, let's move on to our next speaker, who's Tim, who will tell us about how to read a scientific paper effectively. The floor is yours, Tim.
All right. Hello, everyone. How is it going? Let me just share my screen. I'll share that. We'll go to NASA ADS. So the first part about reading a scientific paper is actually finding it. In our field of astrophysics and astronomy, one of the best tools is this NASA ADS. Unlike the previous speakers, I don't have any slides, so this is live. I'm just going to play with this and show you a little bit of an example on how to use it. That link, that URL there, will work in any browser. It's fine. I mean, I use Chrome just because I do. And you can also just Google NASA ADS, and you'll be able to find that. So there's two different ways of using this. You can use either what's called a classic form, which has, fill in the form, press search. The more powerful version, though, is the modern form. So this uses what's called Boolean operators. So you can add in and, or, and not. So you can do things like look for an author. So if we want to do, or a first author, we can choose that. It'll add that. And then add in the year. You can do author, first author, year, and basically build this all up. But what I'm going to show you today is how to find a specific exoplanet system. Everybody has their favorite one. My one happens to be TRAPPIST-1, which is a very close-in system of 7 planets into a red dwarf system. So I'm interested in finding the TRAPPIST-1 paper, the paper that started with it. It starts off everything, the one that I can cite that has 7 planets. I don't want to cite Wikipedia. That's not a good thing. Although Wikipedia is actually a search tool that you can use to find these sort of things. So it says, abstract and title. Let's do that. That looks good. So search abstract title and keywords, which is ABS. So let's go TRAPPIST-1. And we'll do a little search. That's going to pull up a whole bunch of these because it's a very popular thing. So, okay, that's a little bit more than I wanted to find. All right, I don't care about the non-refereed articles, so I'm going to narrow it down a bit by going refereed articles on the side there. Okay, that's still a fair few. Now I'm thinking I want to find the best one, the article that's been cited the most. So a lot of this is about citations. So make sure you read your university guidelines on how to cite. I mark a lot of university papers, and if you can make your markers happy, use the correct citation system. That's a hint for you. So let's go citation count. Let's do that. Look, okay, this one's got 800 citations, so that's been cited 800 times. Okay, that's the one we want. So we click on that, and it gives you basically this overview of this paper. It was done in 2017. It's a Nature paper, so that means that it's got you get to know the different papers that are in your field. There's a lot in A&A, which is astronomy and astrophysics. You also might see Nature. You might see PNAS, which is the National Academy of Sciences, MNRAS, monthly notices of the Royal Academy. There's a whole bunch of them, and various ones are that's a tutorial in and of itself as to which one's best, in inverted commas. Anyway, this is Nature. So let's have a look at this. You've got some things down here. This is a bit of information about the article itself, when it was published. There's some keywords there, ePrint. There's some comments. Here, there's some really cool things here like export citation. this is one of the most useful tools that you can use from ADSO. We'll talk a little bit about BibTeX format when we get to actually looking at LaTeX. So BibTeX is how we do that. Oh, I went wrong doing this request. Export citation. Yeah, there we go. I just opened a new tab. So you can basically, hey, look, there's your BibTeX citation. You don't have to search for it. You don't have to generate it. You copy and paste that into your file format system. Easy. I changed the tag there, but this is one of the main reasons I use NASA ADS these days is finding a file, finding a paper and then actually going and downloading the exported citation. Anyway, back to the actual paper itself. There we go. Back to the paper itself. So it'll have, all the authors up there, which is a lot. There's the title. You can do things in ADS like have libraries. So if you create an account, you can create things like, oh, I want to put this in my TRAPPIST-1 library because I happen to be doing a project on TRAPPIST-1. Anyway, so let's have a look at the actual file itself. I'm going to open that in a new tab. Now, this one would prove a little bit problematic for some people, and I'll show you why in a minute. So this is Nature. Nature is a commercial journal. You can go into your favorite Barnes and Noble. And, I don't want to provide feedback. You go into your favorite Barnes and Noble and literally pick up a copy of Nature. So Nature costs money to access usually. But luckily for a lot of you, you'll have access through your university. There should be a little pop-up that will come up here. You can access that. So you can download the PDF and get the nice, pretty version. So this is literally what it would look like if you went to the shelf and managed to get a copy of Nature from that. For those of you that don't, luckily, most of us have what's called archive. And I'll show you that as well, just as a contrast, because they do look different. So archive is a repository of preprint information. So what that means is at one point during the publication process, the authors will go, I'm going to upload this to archive because I'm a good person and I want people to access this without having to pay for it. So we'll download the PDF of that. PDF software is how most journal articles are distributed. Just make sure you have a good, your standard version of Adobe Acrobat, and you can read that. So this one and this one, these are the exact same article. So if you have a look, the archive one is not as pretty, I would say, as the letter, as the full one. Sometimes they might not have access to the, it's got some, there's a couple of tables. Okay, so it's got, so the archive does have some of all the pretty plots, but they're just not in the right spot. They might have extra information. You might have to turn your head a bit, but sometimes these are actually formatted correct, like almost identically to the actual paper itself. Let's have a look at this one. Let's have a look at this paper. So every journal will have its own format. When you're told to write a paper, you'll usually be told to write, okay, please write an abstract. Here is the abstract of the paper. That is your snapshot of the article. A well-written article, basically you can tell almost everything you need to know in that part there. It should include sort of the cliff note. It's basically cliff notes if you're old enough to remember that version. The next bit will be basically an introduction. This can be, sometimes these are, the introduction is in the, like, Nature articles are slightly weird because they don't have as much of a structure. But what you can do is you can read it and have a look at the background information. Generally, then it goes into, you know, the methodology. Again, Nature papers are a little odd because their methodology is actually as a separate section. So this was just basically in their methods section, they'll describe how they got the data. Sometimes this is actually the most important bit. If you're trying to reproduce somebody, you don't care about the results. You only care about how they did it, or how they did a small part of it. Like if you were trying to reproduce some of these, the TRAPPIST ones results, well, for a start, you need some time on the VLT, which is an 8-meter telescope. Sure, go for your life. You know, this is just basically describing some of all the information. There's some bits of information there. And sometimes this methodology section can actually be the hardest section to read. If you don't care about, you just want to care what they got and how they did it, that's fine. Skip the method section. A lot of people actually sometimes read a journal article back to front. So they'll go, oh, what do I care about? I only care about their conclusions. So, yeah, we found long-term dynamical evolution of the system to be highly dependent on exactable parameters. The TRAPPIST-1 system is a compact analog for the inner solar system. It represents a unique opportunity. Okay, that's the Cliff Notes version. Good, got it. Got the actual information about the TRAPPIST-1 system that I care about. So in that case, some people just jump straight to the conclusions. In between that, you'll have obviously all the results section. You know, we've used the results to observe the investigate the TTV is transit timing variable. You'll figure that out. And numerical n-body integration. So that's what I do. I do the n-body integration. So, okay, that's the n-body integrations. That's like what I care about. Preliminary nature of some of the dynamics. So, you know, which may not correspond to the global minimum. Table 1 shows main planetary parameters. That's what I care about. All I care about is the period of TRAPPIST-1, B, C, D, E, F, G, etc. The 7-planet system. So there's the periods in days. Okay, that's all I care about. That's what I know. Okay, copy paste that into my own journal article and done. Reading it can be a linear thing. A lot of people do read them linearly, but that as you get into the field, you may not actually find that is the correct way to do it. You know, I do journal papers where I might have 100 to 200 references. I tend to over-reference, but I'm not going to say it will take me weeks of my time to read through every little bit of this when all I might care about is the period. So it is fine to skip things. You don't have to read and understand every single little piece of the information. And you know, your stage of your careers in the undergraduate, you probably won't. You know, we note the ratio of masses between the inner 6 planets and the TRAPPIST-1 is around 0.2%, as that is the Galilean satellites of Jupiter. That's cool. Okay, done. Not lock that away in my little brain. You might come back to this, you know, in 2 to 3 years' time and go, yes, that's that really interesting paper I read on TRAPPIST-1, and go into it in more detail. And then so you can find out little bits and pieces about this. Another way to read these is to look at the figures. So Okay. So this is what I want to see. Okay, there's the dips that are B, C, D, E, F, G, and H. Oh, okay, that's interesting. Some of the dips are bigger than others. Some of them are longer than others. That's the architecture and orbital separation. This is what I want to see. This is what I want to look at. Some people just go straight for the figures. And there's a way of writing a paper around a figure. So instead of trying to tell the story of trying to make up, try to say, all right, I got to do an introduction, conclusion. The context can be, all right, I've made this cool figure. Here's my cool figure. All right, now I have to do the background information. Okay, that's the introduction. What does somebody need to know to understand that figure? Then your methods, how you made the figure, the results. Hey, look, pretty cool figure. Discussion, what does the figure mean? Conclusions, hand wavy stuff that says, hey, my figure is cool and it leads to other cool things. So depending on your learning style will depend on how you read a paper. Every single person is going to read a paper differently. So that's what you need to figure out, and what I encourage you to do during this Introduction to Astro course is work out how you read a paper. Do you jump around? Do you read the abstract and go, that's the bit I need to do? Okay, I'll go to the methods. Do you jump in and go straight to the figures? Or are you a linear reader? Do you need to read everything in the paper? Otherwise it will annoy you and you will feel you've missed out on some information. All are perfectly valid. And you may not read the same paper the same way. Some of the papers you may only need a small bit of information. You get that information from the abstract and off you go. So that's how a very brief overview on how to read a paper. On the Intro to Astro 2020, you've got how to read scientific papers. There's some links to that, download and closely reading scientific papers. There's some links. We have a bit of a assignment that I'll need to upload in a bit. So what I want you to do is use the ADS to find the discovery paper for your favorite exoplanet system. You can go to Wikipedia and find a whole list of exoplanets and find one. Doesn't matter which one. Write a very brief description of the article. Choice of your choice, how brief that is. If you want to go in depth in it, that's fine. You should also make a copy of the LaTeX citation, like I showed you before, from here by going to Export Citation. There's your BibTeX citate thing. There's a bit of a side bit to that, or store your article in your favorite citation manager. So up on here we have, we recommend Mendeley as one option. You've also got things like EndNote and a couple of the other ones that are also open source, depending on how you want to go about it. So that is all your task. Find a paper. Try and do a little bit of, and then export it into your citation thing. So, and that's
all right.
That's it.
Thank you so much, Tim. Right, I think we are now at the point for last section of the lecture today, which is our presenter is Jack, who will share with us his life story of how he ended up working as an astronomer. There you go, Jack.
Yes, hi. Thanks. Hi, everyone. I'm Jack. I'm a fourth-year grad student now at University of California, Irvine, where I study exoplanets. But I just want to share a little of my story about how I got to where I am now, because I think there's some, it was not a straight path by any means, and there's some twists and turns, and I think it's important that people know that there's not one path to grad school. There's many paths, many successful paths, And it's important to keep that in mind because the path you might think you have in your head, maybe won't work out, or maybe it will, but it's not right at that time. And so just knowing that there's many paths to grad school, I think is important. So I'll start my story with in undergrad, I attended Emory University in Atlanta, Georgia. And I really loved the school. But I took my first astronomy class there and I was instantly hooked. I knew I wanted to do astronomy after taking this one course, my first semester freshman year. But as I looked more into the astronomy program at the school, the more I looked, the more I kind of thought they don't really have a very strong program in astronomy. And in fact, I had taken half of the classes already that they had offered by the end of my freshman year. And they weren't really doing research. There was not a professor doing active research. And so that was really tough to come to grips with because I knew I wanted to do this, but it just felt like I wasn't quite in the right place to do this and to have opportunities to excel at it. And so I made a very tough decision to apply for transfer. And I was fortunate to get in to a couple schools on transfer. And I ended up choosing to go to Vanderbilt University in Nashville, Tennessee. And at Vanderbilt, I ended up taking more classes, getting more into astronomy, loving it more. And I asked a professor there if I could do research with him. And he said yes. And he really gave me the opportunity and the skills and the mentorship to excel in this field. And so I'm very grateful to him for giving me that opportunity and taking me under his wing in some sense, and allowing me to do this kind of undergrad research, but also to do it at a pace that was reasonable, acceptable for an undergrad. He didn't push me to put out papers and you should be doing this all the time. No, he knew I was an undergrad and that I had other courses and that research was something I was wanted to do on the side, but it was important to me, but it wasn't getting a grade in it. And he knew I wanted to enjoy my undergrad experience as well, extracurriculars, hanging with friends. So he knew I was an undergrad, and I think that was very important. And I think that if you are in undergrad and thinking about doing undergrad research, I think you definitely should reach out to a professor or two in your school, but know that it shouldn't take over your life. You only get to go to undergrad once, and there's a lot of ways to enjoy that experience while also taking on the kind of research that maybe you think you'd be interested in doing more one day and learning about. But I remember at the beginning of my senior year, he called me in his office and he asked me if I wanted to go to grad school, and if so, where I was thinking about going. And I honestly hadn't thought a lot about it at that point. I was not sure if I wanted to go to grad school. I thought I might want to try something else. And I told him that. I said, I think I want to see what else is out there in the world. I've been a student my whole life, from kindergarten up through senior year of college, and I wanted to see what it was like to go out and get a job and work and just kind of see what that aspect of life was like. So he was very accepting of this and supportive. He did tell me, though, and I'll never forget, he said, I've heard a lot of people say that they will go out and get a job and then come back to school later in a few years. He said, I've heard that a lot. And he says, I've never seen anyone do it. And he said, even people with really good intentions, he said, I've never seen them actually come back to school. And that definitely was disappointing to hear, because I did think that one day I would want to go back to grad school. And I was sincere about that. I wasn't just kind of telling him what I thought he wanted to hear. But I took that to heart, and I said, okay, well, if this is something I want to do later, I'll have to be really intentional about it. But he said, of course, it was the beginning of my senior year. He still wanted me in his lab for my senior year. He still wanted me part of his research team, and so I continued. And then when I graduated, I did take a job in the private sector. I worked as a software engineer for a bank, doing software and data engineering for them. And it took me about, I'll say, a year or so of doing this to realize that I really didn't like it. In fact, I really hated it. And right around that first year, I started thinking, okay, it might be time to start exploring grad school again. And the thing about grad school, of course, and this is true for anyone, never mind whether you're coming from undergrad directly or if you're going out in the world and coming back, no matter what your life path is, there are certain deadlines to grad school. You know, the application season is usually in December. And if you have to take standardized tests, which I'm glad that they're getting rid of standardized tests in grad school. But at the time, I still had to take standardized tests. So, you know, those have certain dates and there's certain deadlines. So those were things I had to be aware of. And as I was working, I was trying to also get all these things in order and taking tests and writing essays. And so if you do think you want to go to school, you just have to be mindful of the deadlines that are associated with actually applying to school. You might say, oh, I don't want to go for another year, but that means you have to start the application process now. But so I did all that. I applied to school and I actually quit my job partway through the application process, specifically so that I could focus on applying. And I did move back home with my parents while I did that, which I think was a great thing. I enjoyed it. But then I did get into one school. I applied to 10 schools. I got into one. And that's where I'm at now. I'm at UC Irvine, and I absolutely love it. And I remember I went back to that advisor when I was in that application process. And I said, you know, I'm going to do this. Will you write me a letter of recommendation? He said, absolutely. He was on my team during that application season and rooting for me and advocating for me. And I think he was surprised to see me, you know, as dedicated to it as I was, because again, he said he had never seen someone come back. But so the kind of the point of the story that I want to wrap it up and say that you do not have to go from undergraduate to graduate directly. You can go out into the world, you can take a job, you can, anything you want to do. It can be 1 year, 2 years, 5 years. You can absolutely leave undergrad, go do other things, and come back to grad school or apply to grad school. I just don't want you to think that your path closes because you don't go at a certain time. I know there are graduates in my program who are even older than me, who started after me and are older than me. So everyone has their own life story and path to grad school. There's no one right way to do it. One thing that I might say as a caution, just because I think the truth is important, coming back later after taking a few years off, it will make your first year a bit more difficult. I remember I had to kind of figure out again what it was like to be a student. And I did not do very well in my first classes that first quarter because I was out of practice. I mean, like anything in life, physics and astronomy and math is practice. The more you do it, the better you get at it, the better you understand it. And so having stepped away from it for a bit, I was a little rusty. And so it did take a bit of extra effort to kind of get back to the level that I think my peers were at who did come from undergrad to grad school. So I think that's important to say because it's the truth, but it doesn't mean you can't do it. And it doesn't mean you shouldn't do it. And yeah, I think that's what I wanted to say about that. I just don't want you to think the door is closed.
Mm-hmm. Thank you so much, Jack. That was definitely inspiring.
And I'm happy to talk about it more too. If I mean, my email address is on the Piazza site, I believe.
Mm-hmm. Yeah, we can
so
definitely extend this discussion further.
Yeah, feel free to email me or anything, and I'm happy to talk to anyone about this kind of stuff. I think it's important that we talk about it.
Mm-hmm. Definitely.
Yeah.
Cool. Okay, that's all the topics for today's lecture. Before we end, let me remind everyone to check out our course website for more information for the assignment on GitHub, which is also linked there for the reading assignment. Moreover, I want to say this lecture is probably more information than anybody can take. I know people may get confused seeing some of these for the first time, but the intention is that we show you the resources or the available packages, Python out there. Then you can later go explore these packages or resources yourself, or just pause the recorded lecture halfway and type in the comment in your terminal and see how it goes. Don't be worried that you don't get it for the first time. It's not intended to. think that's all I wanted to say. Let's meet here next week, same time, same place. Meanwhile, if you have time, check out our tutorial and reading assignment. Thank you, everyone. I'll see you next week.